right. Is it okay now? Okay, right, thank you. Yeah, welcome friends to the 11th lecture in mathematics for the GATE students. So we are dealing with complex variables. We just started yesterday. So today I want to finish it off complex variables. And tomorrow, last day, the program is will be dealing with probability. We have very elementary ideas of probability up to theorem. So we will finish it off tomorrow. So we started complex variables, and we have discussed some elementary properties like what is a function of a complex plane, some basic definition, what we call a neighborhood, what we mean by neighborhood, deleted neighborhood, what we mean by function. So these are the things that we are discussing. So once again, you have to understand this idea. So whenever I say w equal f of z is a complex valued function and z is x plus iy, we have discussed the geometry of x plus iy. We can always express it as an organ diagram xy, and x is equal to r cos theta, y is equal to r sin theta, x plus iy becomes r into cos theta plus I sin theta, where r is square root of x square plus y square and theta is the argument that is given by theta is equal to tan inverse y by x. And then De Moivre's theorem and all things, basic things. Yes, then circle is represented. What is a neighborhoods that we need this neighborhood throughout our discussion on complex numbers. If z is equal to x plus iy and z naught is equal to x naught plus iy naught, then z minus z naught is equal to a represents a circle with center at x naught, y naught and radius a. So if you put z and z naught here, this becomes modulus of x plus iy minus x minus iy naught. So that is x minus x naught plus I into y minus y naught modulus, that is x minus x naught whole square plus y minus y naught whole square is equal to a square, which is circle centered at x naught y naught. So if you take any point, if you consider a small circle around that point, alright, take any point, just construct a small circle around that point as center of the circle, okay, then that is called a neighborhood. Then this is the meaning of a complex valued function. W is equal to f of z, and z is a function of xy, x plus iy, then u of xy plus I into v of xy, because f of z is a complex valued function. That means it gives a complex number. So output is a complex number, input is a complex number, z is equal to x plus iy, and output is also a complex number of the form x plus u of xy plus I into v of x, may be a function of x and y. If that is the case, what exactly is, we have in z plane x-axis, y-axis, and any point is expressed as a complex number, x plus iy is expressed as a denoted by a point here. Okay. Now, if you consider the function f of z, that means if you at this point the function gives another complex number, f of z naught becomes another complex number. Call that as w naught. So w naught also contains some real part and imaginary part given by u of x naught y naught plus I into v of x naught y naught. That is the point. So if you consider, imagine a u axis and v axis, then we call w plane, because u and v are the real and imaginary parts. Consider a u axis and v axis. This w naught becomes a new point in this uv plane, and this uv plane is called w plane. So what do you mean by this function now? This function f of z transforms the points from our usual xy plane to w plane. So function is a mapping from xy plane, that is z plane, to w. And that we have to. So very much similar to our real valued functions. 1 plus z square by 2 factorial plus z cube by 3 factorial, so on and so forth. From that we can write sin z is e power ij minus ij by 2i. Cos z is e power ij plus e power minus ij by 2. So these are the important relations we have. Sin ix is I sin hx, sin hix is I sin x, cos ix is cos hx, cos h to ix is cos x, tan ix is I tan hx, and tan hix is tan x. Then coming to the limits, we have seen along different paths the limit it must exist, and all the limits along all different paths they must be equal. Then we say that the function has a limit. So we have to see in these relations. Then continuity. This is where we stopped yesterday. A function f of z is said to be continuous at z is equal to z naught if limit z goes to z naught. F of z is equal to f of z naught. Or a function f of z is more rigorous in mathematical rigor. A function f of z is continuous at z naught if corresponding to each epsilon there exists a delta such that modulus of f of z minus f of z naught less than epsilon whenever mod z minus z naught is less than delta. So f of z is continuous in a domain. It is continuous at every point of the domain. Say for example, if you take a domain like this, at every point if it is continuous, we say it is continuous over the domain. And if f and g are continuous at z naught, then f plus or minus g, f into g, f by g, g naught equal to g 0 are also continuous functions. If f of z is continuous at z naught, then so is modulus of f of z. So let us say, check a couple of problems. If f of z is equal to z bar by z, where z is x plus i1, x minus z bar is x minus i by. Z bar means conjugate of z. That means the mirror image of this x plus i by about x is equal to 0. So f of z is x minus i by x plus i by. So limit z goes to 0, f of z becomes limit x tends to 0, y tends to 0, x minus i by x plus i by. So if you take the limit, it becomes minus 1. And if you take the limits, reverse the limits, this becomes 1. Yes. So that's all we have discussed. Now, we start this definition today. Derivative of a function, complex valued function. A function w is equal to f of z is said to be a differentiable at z is equal to z naught. Here, z is an independent variable, f is a dependent variable. Z means z is a function of again x and y, z is equal to x plus iy. So what are the independent variables? X and y are independent variables. F depends on x and y. So, but anyhow, because w is a function of z, we first start with f of z. Is said to be a differentiable at z is equal to z naught if the limit delta z goes to 0, f of z plus delta z minus f of z by delta z exists, and it is denoted by f dash z naught. The definition is very much similar to what we have learned in ordinary differential calculus. So f dash z naught is limit z tends to z naught f of z minus f of z minus z naught. Either way you can write the definition of a derivative. So in ordinary calculus we stop with the derivative and then we don't there is next section is integration. So but here it's not so. There is, because we are talking about domains, there are so many things to discuss. And some rules on differentiation, the dy dz of a f plus or minus b into g, where a and b are constants, maybe complex constants, is equal to a into f dash z plus or minus b into g dash z. And dy dz of f into g, it's also u form same thing, f into dg by dz plus df by dz into z, and dy dz of f dash g, f by z is d into df by dz minus f into dz by dg by dz by g square. This is also u by v formula, quotient rule. Then dy dz of z power n, it is n into z power n minus 1. Is also usual calculus, same thing. dy dz of fz whole power n, this is n into f of z whole power n minus 1 into df by dz. Then comes the chain rule. If you have w is equal to f of z and z is g of z, then dw by dz is, because w first is a function of z, dw by dz by dz. So this is chain rule. The similar structures we have already seen, similar formula we have already seen. So it's not a difficult job for you to remember these things. So let us do some problems on this differentiability. If f of z is equal to z bar, is it differentiable? Okay. So let us say x plus iy, z is equal to x plus iy, then f of z becomes z conjugate, that is x minus iy, and delta z is delta x plus I delta y. Then f of z plus delta z becomes, because I want this for differentiation, f of z plus delta minus f of z is what I want. So f of z plus delta z is, if the change in x is delta x and change in y is delta y, this becomes x plus delta x minus I into y plus delta y. So if you consider this now, f of z plus delta z minus f of z by delta z, this will be delta x minus I delta y by delta x plus I delta y. Now if you take the limit delta z goes to z, this is the condition, this limit must exist. So this delta z goes to 0, it can happen two ways. First delta x goes to 0, then delta y goes to 0. And then otherwise, first delta y goes to 0, then delta x goes to 0. And these two limits must be equal. So in the first case, delta x goes to 0 and delta y goes to 0. That is, this is the function. So put delta x is equal to 0. This becomes 0, this becomes 0. Minus I delta y by I delta y. So if you cancel everything, then you get minus 1. So if you reverse the limits, then delta y goes to 0 and then delta x goes to 0. And delta x minus I delta y by delta x plus I delta y. And delta y goes to 0, these two things become 0. So you are left with limit delta x goes to 0, delta x by delta x, that is 1. So here the limit is minus 1, here the limit is 1, so the limit does not, they are not equal. So that means whenever the limits along different paths are not equal, we say that limit does not exist. When the limit does not exist, f dash z does not exist. So your function f of z is equal to z conjugate is not differentiable anywhere. Okay. Next one. F of z is equal to modulus of z square. Discuss the differentiability. As usual, z is equal to x plus iy. So mod z square is, you can write it as always z into z conjugate. Okay. So f of z plus delta z becomes z plus delta z into z conjugate plus delta z conjugate from this. Then you expand this like this. So then f of z plus delta z minus f of z by delta z, construct this. So that means if from this z plus delta z, because z into z conjugate is f of z, that will be cancelled, the remaining expressions will be z into delta z conjugate plus delta z into z conjugate plus delta z into delta z conjugate by delta z. Now as delta z goes to 0, that means delta x goes to 0, delta y goes to 0. If we expand, if substitute x plus iy in delta x minus delta iy and all that stuff, because z is x plus iy, z conjugate is x minus iy, delta z is delta x plus I delta y, and delta z conjugate is delta x minus I delta y. You put these things now here, this is what we have, big expression. Okay, then first limit delta y goes to 0. If you consider limit delta x goes to 0 and make all these delta x tends to 0, the remaining expressions, this is the remaining expression. Now if you consider limit delta y goes to 0, then this expression will vanish because delta y going to 0. In other terms, we don't have delta y terms. So the limit is y plus I by I, because one I missing here. Okay, I. Right. Now reverse this limiting process. That means first delta y goes to 0, then delta x goes to 0, or the whole function. Then this is what we get: x plus delta x, sorry, x into delta x plus x into delta x plus delta x into delta x. We don't have conjugate terms here because I terms are not there in x by delta x. If you cancel this delta x terms and in the remaining expression, if delta x tends to 0, this is what we get: limit delta x goes to 0, 2x plus delta x is equal to x. Now what are the limits here? This is 1 plus I by I into y, and in the second case it is 2x. This is y and this is in terms of x. They are completely independent. They are never equal. So the limits are never equal. Only case when they are equal is when x is 0 and y is 0. When x is 0 and y is 0, this becomes 0, this also becomes 0. In only that condition, these two limits will be equal. So what does it mean? Right. Sorry, somehow it's going back. Yeah, this is function of y and this is function of x. They are equal only when x is equal to, limits are not equal, but at z is equal to 0, that means x is equal to 0, y is equal to 0, they are equal. That is the only case these limits are equal. So derivative exists only at z is equal to 0. At all other points the limits are different, so it does not exist. Only at z is equal to 0 it exists. So now we have defined the derivative at a point. The derivative at a point only. Now what is the extension of that? That is analytic functions, because this is the heart and soul of complex functions. Analytical functions is a heart and soul of complex variable theory, because everywhere in every statement we use these analytical functions. You have to understand this analytical function very clearly. So a function f of z is said to be analytic at a point z0 if f is differentiable at z0. It means f must be differentiable at z0 and at every point in the neighborhood of z0. So differentiation at a single point. Okay. So consider a small neighborhood of the point, small circle around the point centered at z0. Okay. And now if the function is differentiable at every point of this neighborhood, not only the point z0, at every other point of the neighborhood of z0, then it is called analytic. Once again, differentiability at a point and analytic behavior in the neighborhood, differentiable at every point in the neighborhood of z0, that is analytic behavior. So it's a more general thing. At one point, if it is differentiable, it's not enough. In the neighborhood of that point, throughout the neighborhood of the point, the function must be differentiable. Then we say that it is analytic function. And then the entire function, still an extension of that. A function which is analytic everywhere, the whole of z plane, take any point. If the function is an analytic function, then it is called entire function. The best example is e power z. There is no failures. Complete z plane, take any point, the function must be analytic. Where it is going? Okay. Let's do some problems on this. Yes. And then we have, then how to check the analytic behavior of a function. So I said it must be differentiable at each and every point of the neighborhood. How many points do we have in the neighborhood? We have infinite number of points. So do we test the differentiability at each and every point? No. So there must be a test to check whether a given function is analytic or not. And you have very powerful and wonderful conditions to check the analytic behavior of a function. They are called Cauchy-Riemann equations. We have some necessary and sufficient conditions here. So this is very important theorem. The necessary and sufficient conditions for a function f of z is equal to u plus iv to be analytic. Say if I give a function f of z is equal to u plus iv, then to test whether it is analytic or not, you have to check these two conditions. What are those two conditions? Dou u by dou x, mind you, these are necessary and sufficient conditions. So that means whenever f is analytic, these conditions hold good, and whenever these conditions hold good, f will be analytic. For a function f of z u plus I plus v iv will be analytic or 1 dou u by dou x plus dou u by dou y, dou v by dou x and dou v by dou y are continuous functions of x and y. That means real and imaginary parts of the given function has continuous first order partial derivatives. Second condition is dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. These two equations together are called Cauchy-Riemann equations and shortly CR equations. Cauchy-Riemann equations are CR equations. Dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. So, my dear friends, most of the students, what the mistake they commit is when they check the CR equation, when the function is given, they check the CR equations. If they are satisfied, they say it is analytic. No. CR equation must be satisfied, and then you have to check whether the first order partial derivatives are continuous or not, because the necessary and sufficient conditions are two conditions we have. So if F is analytic, these two things will happen, but together should happen. First partial derivatives must be continuous, and the CR equations dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x, they must be satisfied along with the continuity of first order partial derivatives. So be careful with this. Whenever you want to test it, you have to test both the things. So if F is analytic, implies CR equations are satisfied, and that's why I'm writing it very clearly. If CR equations are satisfied and Ux, Uy, Vx and Vy are continuous, implies F is analytic. You have to check both the conditions. And then one more important results of analytic behavior, harmonic functions. If F is equal to U plus Iy is analytic in a domain D, then U and V satisfies the Laplace equation. They satisfy the Laplace equation. So that is Laplace equation. We know that dou square u by dou x square plus dou square u by dou y square is equal to 0, and dou square v by dou x square plus dou square v by dou y square is equal to 0. My dear friends, now we have to learn how to link one idea with other idea. Where do you come across the Laplace equations? In heat conduction, steady state conditions in 2 dimensions and partial differential equations. So there must be a relation between the complex numbers, analytic functions, and then diffusion equations. Okay, so this complex idea, this analytic idea is useful there also in diffusion equations, fluid mechanics, and conduction of heat in 2 dimensions. And so this Laplace equation is same as the Laplace equation, right? Okay, and what is harmonic function? Any solution of the Laplace equation is called a harmonic function. So whenever F is analytic, it can be a short answer. It can be a very nice question for you. In if U plus IV is analytic function or F is analytic, then real and imaginary parts are 1. Harmonic, 2. Oscillative, 3. Non-harmonic, 4. Homogeneous. Nice. Okay. Straight away you can write they are harmonic. Otherwise, you can ask the question may be like this: F is equal to U plus IV is analytic in a domain D, then U and Y satisfy Poisson equation, Euler equation, Lagrange equation, Laplace equation. Straight away the answer for the question is Laplace equation. They satisfy the Laplace equation, and the solutions of the Laplace equations are called harmonic functions. So, and U is known as conjugate harmonic of V, and the vice versa. That means V is called harmonic conjugate harmonic of U. And another important application is orthogonal trajectories. If F is equal to U plus IV is analytic, then the families of curves U of xy is equal to C1 and V of xy is equal to C2 are mutually orthogonal. That is, if U is equal to C1 or orthogonal trajectory of V is equal to C2 and vice versa. What do you mean by orthogonal trajectories? That you have to understand first. So as I said earlier while discussing very first classes, C is an arbitrary constant. Whenever C is an arbitrary constant, you go on giving different, it's not a constant, arbitrary constant. There is a lot of difference between constant and arbitrary constant. If it's an arbitrary constant, go on different values to C, then that a family of curves or surface may be generated, because a 2-dimensional thing, x and y independent variable surface is generated. Similarly, if you go on giving different values to C, we get surface, another surface. So these two surfaces are orthogonal trajectories of one another. What do you mean by orthogonal trajectories? At any point, you draw a tangent to the surface, they are perpendicular to each other. Or draw a normal to the surface. This is let us say, so this hand is a surface and it's an outward normal. This hand is under surface and you take this normal. This normal means outward normal perpendicular surface. This is second surface and its normal is like this. If you find the angle between these two normals, they are perpendicular. Okay, that is the geometry of U and V. They represent always orthogonal trajectories of one another. And what are the equations of, because we have been discussing this polar curves and it is a very, very important idea for ECE people, EEE people in their phase shift and all that they do. So polar form of square equations, if Z is equal to x plus iy, we have seen that x is equal to r cos theta and y is equal to I sin theta. We have seen in the very first class. So that is r into cos theta plus I sin theta is e power I theta. This is r e power I theta. Or we write f of z is equal to f of r e power I theta. This is polar representation of f function. Then f of r e power I theta is, you call this as, because it's a complex valued function, it has a real part and imaginary part, call them as u of r theta, I into v of r theta. U and v are functions of r and theta. Then CR equations in polar form are dou u by dou r is equal to 1 by r dou v by d theta, and dou v by dou r is equal to minus 1 by r dou u by dou theta. These are called CR equations in polar form. Now, do some problems. Discuss the analytic behavior of f of x, f of xy, f of z or f of xy, whatever you take here. Square root of xy. Square root of xy at 0, 0. Given that CR equations are satisfied. Mind you, I have given that CR equations are satisfied. Now I am asking you whether it is analytic or not. Then what you have to test? We have only two tests here. One is CR equation must be satisfied, and the first one is first order partial derivatives must be continuous. So it is given that CR equations are already satisfied, then you have to check the second condition. Since CR equations are satisfied, ux is equal to uy and uy is equal to minus vx, these are CR equations. And f dash x, two things might happen here. First order partial derivatives must be 0, must be continuous, and f dash z must exist. F dash z must exist. F dash z means dou u by dou x and dou u by dou x exist continuous. So f dash 0 is limit z goes to 0, f of z minus f of 0 by z. So limit x goes to 0, y goes to 0, f of z means square root of xy, f of 0 becomes 0, by z means x plus iy. First, let us say x goes to 0. So this becomes 0. Okay, very good. And first let this y go to 0 and then x go to 0. Again, square root of xy by xy minus 0 by x plus iy. Again, when y goes to 0, the whole thing becomes 0. So both the limits are equal. It's not enough. You have to check along other curves also. Let us say y is equal to mx and x goes to 0. So if you put y is equal to mx here, this becomes x into yx. That means square root of m into x square, and take x out. And in denominator also x plus I into mx, you can take x common. If you cancel x, what happens? Then is independent of x, and then limit x goes to 0, it becomes square root of m by 1 plus im. Is it 0? It's 0 only when m is equal to 0. But m is equal to m is guaranteed? No. M is an arbitrary constant. It depends on the value of m. As m takes different values, you get different values of the limit. So limit is not unique. It's not the same with the other things along other paths, and it is also not a constant. It is changing with respect to m. It's an arbitrary constant parameter. So it's not unique. Then f dash z does not exist. So the irony here is CR equations are satisfied, but f dash z does not exist. This is one way. The other way is, what is dou f by dou x? F of z is, the imaginary part is 0 here. What is the first order partial derivative with respect to x? 1 by square root of y by 2 root x. At x is equal to 0, what happens? It becomes goes to infinity. It does not exist. So that means the first order partial derivatives are not existing, are not continuous. So though these CR equations are satisfied, the function is not analytic here. Find the values of k such that f of z is equal to e power x cos ky plus I into sin ky is analytic. So e of xy is equal to e power x cos y. So real part is e power x cos y cos ky. V of x is equal to e power x sin ky. So dou e by dou x is a function of y. So e power x derivative e power x into cos ky. And it must be equal to v of y as per CR equations. What is v of y? Dou v by dou y. So e power x is constant with respect to y. So e power x into sin ky derivative is k into cos ky. So these two things must be equal. So cos ky, e power x is e power x, same thing. So cos ky is equal to k into cos ky. So cos ky, even if you cancel cos ky, so k must be equal to 1. Then similarly check whether any other k exists with using this other CR equations. Dou u by dou y is e power x into cos ky derivative is minus k sin ky is equal to dou u by dou y is equal to minus vx. That is minus vx is minus e power x sin ky. You observe the terms here. E power x can be cancelled, sin ky cancelled. So k is equal to 1. So k, that means in both the cases the value of k is 1. So for k is equal to 1, this function will be analytic. This is the type of questions, simple questions that might be asked in the examination, finding the k values and other things. So if f of z is equal to xy square into x plus iy by x square plus y power 4 and z not equal to 0, and is 0 when z is equal to 0, and CR equations are given that CR equations are satisfied. Now you have to test whether it is analytic or not. Maybe the question may be asked like this: f of z is so and so, CR equations are satisfied, then the following holds good. F is not analytic, f is analytic. Next one is f is analytic everywhere, and f is analytic only at z is equal to 0. Different options may be, right? So for that again, what I do is I consider f dash z. What happens to f dash z? Does it exist? Just like in the previous problem. That means limit z goes to 0, f of z minus f of 0 by z. Limit z tends to 0 means x goes to 0, y goes to 0. F of z is this one, xy square into x plus I by x square plus y power 4. F of 0 is given as 0 here. The function is 0 and z is 0. By z is x plus iy. So in the numerator we have x plus iy, denominator x plus iy. If you cancel them, then this is the expression. So x goes to 0, this integral becomes 0. Similarly, if y goes to 0, x goes to 0, xy square by x square plus y power 4 also, then when you put y is equal to 0, it becomes 0. So in both the cases, the limit is 0. Not enough. Then let us consider along the straight line, y is equal to mx and x goes to 0. Then I said only x goes to 0. When x goes to 0 along y is equal to mx, what happens? And when x goes to 0, y also goes to 0. That's what I mean. So limit y goes to y is equal to mx and x goes to 0. That means substitute y is equal to mx here. X into m square x square, that is m square x cube by x square, y power 4 is m power 4 x square, m power 4 x power 4. So I can take x square common in the denominator, I can cancel x square, and in the numerator still I have 1x, so that becomes 0. So still the limit is same in both three cases. Let us consider, I told you 5 different paths. Okay. Just I go back once and see to tell you. Yes, these different paths. First we have seen like this, then like this, then y is equal to mx like this, and then I am going with the parabolic paths. Okay. Hope you got. Along all these 5 different paths, we have to find the limit and show that they are all equal. Right. Then we are dealing with this problem. So along y is equal to mx also we are having a 0 limit. Still all the 3 cases okay. Then consider this path x is equal to my square. Then x is equal to my square and then y goes to 0. And then y goes to 0, x also goes to 0, no issues. So this function xy square by x square plus y power 4 becomes, when we put x is equal to my square, m into y square m y power 4 by x square is m square y power 4 plus y power 4. If you take y power 4 common, cancel, we get m by m square plus 1, which may not be equal to 0, the same thing. It depends on the value of m. If you change the value of m, the limit changes. So that means the limit is not unique and f dash does not exist and then not analytic. Do the real and imaginary parts of f of z is equal to z cube cut orthogonally? This is an indirect question. What exactly he wants is, do the real and imaginary parts of f of z cube cut orthogonally? What is the result we have? Whenever f of z is orthogonal, u and v are orthogonal trajectories. So if you show that this is analytic function, then you can say they cut orthogonally. So f of z is equal to z cube is analytic. The real part will be, because it's a polynomial function. You need not even check it. This polynomial function is always analytic and differentiable. Then it is analytic. So real and imaginary parts of analytic function are orthogonal trajectories of each other. There ends the question, simple. Is f of z is equal to e power z entire function? Entire function means it must be analytic throughout the z plane. Everywhere, take any point, it must be analytic there. So f of z is equal to e power x, because z is x plus iy, you can write e power x plus iy, or is e power x into cos y plus I sin y, e power iy is. So u is e power x cos y and v is e power x sin y. So dou u by dou x is e power x cos y, dou u by dou y is e power x into minus sin y, that is minus e power x sin y. Dou v by dou x is e power x sin y and dou v by dou y is e power x cos y, and then they are equal. They are equal. Okay. They are equal. And then CR equation is satisfied for all z. It's not enough. Then for partial derivatives, are they continuous? That is important. So e power x function is always continuous and differentiable. Cos y and sin y are always continuous and differentiable. Then ux, uy, vx, vy are all continuous functions. So then CR equation is satisfied and partial derivatives are continuous. Therefore, e power z is analytic everywhere, or else it is called an entire function. Next problem. Is u is equal to e power minus x into x sin y minus y cos y harmonic? So harmonic means they must satisfy Laplace equation. Dou square u by dou x square plus dou square u by dou y square is equal to 0. ux square plus uy is equal to 0. It is called harmonic. Then ux is, find the first partial derivative, e power minus x into so on and so forth. Similarly, uxx also find it. Very long expressions, you can check it. I need not read everything. You can, when I leave the PPT, you can check it. I can go through it thoroughly. Then similarly, dou square u by dou x square, find it. Then uy, partial derivative with respect to y of this, and then dou square u by dou y square. So if we add both the things, these two things, these things, so like arrow marks like this, they are similar thing, x sin y minus x sin y. If it's from right to left, 2 sin y minus 2 sin y. Circle functions, these things. So everything is cancelled, so we are left with 0. So dou square u by dou x square plus dou square u by dou y square is equal to 0. Hence u is harmonic function. And then, so in this problem itself, only u is given to you. Now, question now is, when only real part is given to you, can we identify whose real part it is? That means, can we construct the function from that real part or imaginary part? That is the question. So, for that, we need only one condition. If we know that the unknown function f of z is analytic, right, and u or v one of these two things is given to you. We know that this is the real part or imaginary part of an analytic function. Then what is the other part? That means if the real part is given, how to construct the imaginary part, or if the imaginary part is given, how to construct the real part, provided u plus iv is analytic. That is what we do. We have very important theorem, Milne-Thomson method. Just I will tell you how to do this problem. I need not go to the proof and all that. Milne-Thomson method says, first thing is, if f of z is equal to u plus iv, then df by dz or f dash z is the standard expression. You can remember this. Very important principle. Underline it. So f dash z is equal to ux plus ivx or ux, and because why we are changing it to u is only u is given to you. V is not given. So everything in terms of u I require u or v. Maybe u is given or maybe v is given. Let us say I am assuming that u is given. So I want to transform, I don't know vx, so I want to transform everything in terms of u. So ux plus what is vx? Because then it is given as fn is a function is an analytic function, so CR equations are satisfied. So vx is equal to minus uy by CR equations. So now f dash z is expressed completely in terms of u only, partial derivatives of u only. So ux minus iuy. Similarly, you can write the in terms of v also. This is do vx plus iu ux. You can do that in terms of v also. So once you write this, then replace z by z. This is the Milne-Thomson method. In this f dash z, replace x by z and y by 0. Replace x by z and y by 0. Ux and uy are functions of xy. In that, replace x by z and y by 0. What we get is f dash z is equal to, call this as phi 1 of z comma 0. That means this, I am calling this after this change, I am calling this as phi 1 of z0 and this is phi 2 of z0. So f dash z, these are functions of z only. So the fz can be obtained by simply integrating this. This method is called Milne-Thomson method. If you do the couple of problems, you will understand very easily. They find the analytic function whose real part is so and so. U is given to you. Then what is the analytic function? So as I said here, u is given to you. So f dash z is dou u by dou x minus I into dou u by dou y. So what you need, first thing is you have to calculate ux uy. Ux is e power x into, you simplify this, this is what you get. Okay. And uy is, this is what you get. So f dash z is ux plus ivx or ux minus iuy in terms of u. So if you put and you write this f dash z and then replace x by z and y by 0. So in this, if you replace x by z, e power z, y by 0, so cos y is 1, z square, y is 0, 2z. So e power z into z square plus 2z. What happens here? Y by 0, so sin y is 0, y is 0, everything, this term is 0. And coming to this, what happens? Z square e power z, y is 0, this term becomes 0, sin y becomes 0, and then y becomes 0, this becomes 0. So only term we get here is z square e power z. Okay. So we get f dash z is equal to e power z into z square plus 2z, or f of z. If you integrate this, we get z square e power z plus c. So v is equal to x square minus y square plus x by x square plus y square. Find the analytic function. Now v is given to you. F dash z is equal to ux plus ivx. So ux is vy. So f dash z in terms of v is dou v by dou y plus I into dou v by dou x. Consider dou v by dou y and dou v by dou x from this 2x plus x square y square whole square into y square minus x square. Vy is so on and so forth. Replace x by z, y by 0. X by z, it becomes 2z, and this becomes minus x square minus z square by z square whole square. That means 1 by z square. And this becomes y is 0 means this is 0. This is also 0. Okay, so f dash z becomes I into 2z minus 1 by z square. If you integrate this, integral of 2z is z square, integral of minus 1 by z square is 1 by z. So simple. So Milne-Thomson method is very much useful for us to identify the analytic function when the real and imaginary parts are given. In almost for all the examination where this complex variable function is there, you have 25% of chances of having a question from this Milne-Thomson method, mind you. Very important idea. Then we move to complex integration. So we have a most important results in complication, that is Cauchy's theorem. Before going to Cauchy theorem, we have, let us see what is how to find line integral in complex valued functions. Consider f of z is equal to u plus iv between a lies between t lies between a and b, where x is equal to x of t and y is equal to y of t is the equation of curve in parametric form. Okay, then integral b a to b f of z dz is equal to from integral from t from a to b f of xt plus I into v of t dx by dt plus I dy by dt. So forget about this simpler way. Integral a to b f of z dz is if f is u plus iv like this, then u plus iv into z is x plus iy. So dz becomes dx plus I dy. So this is what we have. If you multiply these two things and separate the real and imaginary part, real part is u dx minus v dy plus I into v dx plus u dy. From okay, evaluate integral c f of z dz. F is equal to y minus x minus 3x square y, 3x square I, and c is the straight line joining z is equal to 0 to 1 plus I. First we have to understand what is z is equal to 0 and 1 plus I. Z is equal to 0 means x is 0, y is 0, and z is equal to 1 plus I means x is 1, y is 1. So we are joining the 2 points 0, 0 and 1, 1. So the straight line is passing through origin. So equation is y is equal to x. Okay, that is very important. So u plus iv into dz is u plus iv into dx plus I dy. So u dx minus v dy plus I into u dy plus v dx. So this is y minus x dx, that is u. So like this minus v 3x square minus v dy is minus y 3x square dy plus I into u dy plus I into v dx. This is what we have. Points are, that is 0, 0 and 1, 1. Equation of straight line is y is equal to x between these 2 points. So dy is equal to dx. So y is equal to x and dy is equal to dx. You substitute these things in this integral. So this becomes y minus x becomes 0 because y is equal to x. This becomes 3x square dy. X frame changes from 0 to 1 because this is. And then again y minus x becomes 0. This is minus 3x square into I dx. So x cube minus ix cube, if you integrate between 0 and 1, this is what we get. Evaluate integral c f of z, where f of z is equal to z minus 1. C is the arc from z is equal to 0 to 2, and c is the semicircle z minus 1. This is c. Okay. So c is mod z minus 1 is equal to mod e power I theta is equal to 1. This is what we have. Z minus 1 is equal to e power I theta. If you take c, modulus of z minus 1 is equal to e power I theta, modulus of e power I theta is 1. So semicircle from, that means theta changes from 0 to pi. Okay. So z is equal to 1 plus e power I theta. So dz is I e power I theta. So integral over c f of z dz is integral over c z minus 1 dz, integral over pi z minus 1 is e power I theta. dz is I e power I theta d theta. So I into e power 2 I theta d theta, or I into e power 2 I theta is cos 2 theta plus I sin 2 theta. If you integrate, the integral becomes 0. And next one is integral over c x square plus I y x. C is given by parametric form, x is equal to t, y is equal to t cube from 1 1 to 2 8. Clearly x is t, y is t cube, and if we observe the points 1 1 and 2 8, x is changed from 1, x is t is equal to 1, x is 1, t is equal to 1, y is equal to 1. Here t is equal to 2, x is 2 and t is equal to 2, y is 8. So t change from 1 to 2. So dz is dx plus I dy. So put these things, x is equal to t, y is equal to t cube, and dx is dt, and dy is 3t square dt. This is what we have, these relations in this. So this becomes t square plus I into y, t cube into t power 4 plus dx is dt plus I plus 3it square into t. You simplify this and integrate this between the limits 1 to 2, we get this answer. This is how we calculate line integrals in complex valued functions. Then comes the most important result, that is Cauchy's theorem. Cauchy's theorem, in fact, it changed the whole process of complex integrations and the theory of complex integrations. So what it says is, if you understand Cauchy theorem, most of the problems, whatever problems we have done earlier, they become very simple once you know Cauchy's theorem clearly. So what it says is, if f of z is analytic in and on a simple closed curve, that means if you consider a simple closed curve like this, okay, like this is a simple closed curve. So if f of z is analytic inside everywhere and also on the curve, at all points inside the curve and on the curve, then integral over c f of z dz becomes 0. That straight away you can write. You check the CR equations, you check the partial derivatives are continuous, then integral must be 0. Nothing you need to evaluate anything. That is the importance of Cauchy's theorem. If f of z is analytic throughout a simply connected region D, then for any closed contour C within D, then integral over C f of z dz is 0. So if C is a closed contour, so you understand here, okay, if so this is what we mean, right? So if C is a closed contour here, and assume that there are no other curves inside C, then F is throughout analytic, okay? Even inside C1, C2, C3, if it is completely analytic everywhere within C, the integral over C f of z becomes simply 0. Okay. Now the extension of that is, what happens if there are some points within C where the function is not analytic? If C is a closed contour and C1, C2, C and B, a finite number of closed contours interior to C, such that interiors don't have any point connected region. So such a region is called the shaded part in blue color. This is called multiply connected region. They're not simply connected region. This is called multiply connected region. So C1 is a circle here. That means you have a metal sheet, have some holes in it. Okay. Then you pull out those parts. Okay. Then there are some holes in the metal sheet. So that's a multiply connected region. Right? There are some holes in the sheet. If it is completely a metal sheet without any holes, then it's a simply connected region. So it is now a multiply connected region like this. So what is a Cauchy's theorem for multiply connected regions? So to prove this, we need to construct these cross cuts and all that. We are not interested in that, going to the proofs of that. Just take the result. If F is analytic in a multiply connected region, that means within C but not on and outside C. That means F is analytic only in the shaded part. Okay, it's not analytic in this region. That means C1, let us say, is a pole. We delete a small neighborhood around C1. Similarly, if you have another pole here, consider a small neighborhood, pull out the neighborhood from the sheet plane, that is under C2, like that. Okay, then integral over C f of z dz is integral over C1 f of z plus integral over C2 f of z plus integral over Cn f of z. This is Cauchy's theorem for multiply connected region. Then find integral over C dz by z minus a, where C is mod z minus a is equal to r. And mod z minus j is equal to r means a circle equation centered at a and radius r. Or else any point z on the circle is given as z is equal to a plus r e power I theta, or dz is equal to Ri e power I theta, because a is constant, derivative becomes 0. So it is a circular region, so theta changes from 0 to 2 pi. You put all those things in this, so integral over c dz by z minus a becomes theta from 0 to 2 pi, dz is Ri e power I theta, z minus a, because z is a point on the circle, z minus a is R e power I theta. So e power I theta r and cancel, I into 0 to 2 pi d theta, that becomes 2 pi I. Evaluate e power 3z by z minus 3 when z is equal to 1 by 2. So this figure is like this, e power 3z by z minus 3 is analytic in mod z is equal to 1 by 2. Why? At z is equal to 3, what happens? The function goes to infinity. That is a singular point. At z is equal to 3, function is not integrable function. Okay. So, but what happens? Z is equal to 3 somewhere here. And what is your circle? Your circle is mod z is equal to 1 by 2. What is the center? 0, 0. What is the radius? 1 by 2. So, if you draw the circle like this, and you are asking the analytic behavior of this function only in this circle, z is equal to out, z is equal to 3 is outside the region, we don't care about this point. We can neglect that. So, in this region, this function is analytic. So, whenever the function is analytic, the integral becomes 0 by Cauchy's theorem. Integral over c f of z dz becomes 0. So that's why you need not evaluate anything. If you know the function is analytic in a region, you can straight away show that it is analytic in the region by considering all the points, singular points, and if all are lying outside, the function becomes analytic. If some of them lie inside, what happens? We have to learn. Result. If f of z is analytic, integral a to b f of z dz is independent of the path connecting a and b. Mind you, again we have studied this result, similar result in vector calculus. When vector point function f bar is rotational field, then curl f becomes 0. Sorry, irrotational, curl f becomes 0. Then we can always, the path is, the integral is independent of the path taken. Conservative field we have studied again. We are having here integral a to b f of z dz is independent of path connecting. So if you go a bit left, then you can find a relation between, you can convert those things into these things into those things. That is, in a plane you can do it. Because in vector calculus we deal with 3-dimensional geometry also, but complex space is 2-dimensional. If you restrict that to 2-dimensional thing, you can see some relation between these integrals and those integrals. If f is analytic in domain D, a and b are within D, then integral over c f of z dz depends only on endpoints a and b, but not on arc. You can have like this, you can have like this, you can have like this, you can have infinite number of curves. Don't worry, the integral depends only a and b only. These are all important consequences of Cauchy's theorem. And now I said, in this problem, see, z is equal to 3 is outside the region, so integral function is analytic completely and integral is 0. Let us say, if I take in the denominator z minus 1 by 4, 3 is outside, okay, leave it. Take another point inside the circle. So if I say, for example, the radius is 1 by 2, if I take the denominator z minus 1 by 4, so the function is e power 3z by z minus 1 by 4. Where is this z is equal to 1 by 4? Inside the region. Now you cannot neglect it. Neither you can apply Cauchy theorem. What is Cauchy theorem? When function is analytic, it becomes 0. So it's not analytic now. Z is equal to 1 by 4 is inside the region. So now for that type of functions, we have to learn Cauchy's integral formula. This will be helpful to us to solve those equations, to solve those integrals. Let f of z be analytic function everywhere on and within a closed curve C. If z is equal to z naught is any point within C, f is analytic in the region, but in the denominator there is some point which is giving us some problem, that z minus z naught is going to 0. The denominator goes to 0, that's a problem. So if z is equal to z naught is any point within C, then integral over C f of z by z minus z naught is equal to 2 pi I into f of z naught. This is exactly what is the problem I am telling about. F of z by z minus 1 by 4. F of z by z minus some z naught. So if these side of integrals can be straight away calculated using f of z naught. So in this problem what happens? If it is z minus 1 by 4, this integral becomes 2 pi I into f of 1 by 4 straight away. 2 pi I into e power 3 by 4, that is the answer. Just by looking at the problem, you can tell the answer, this integral, without evaluating. Simply put the point in f of z here, multiply with 2 by a, that is our answer. Generalization, say for example, if not z minus z naught, if you have z minus z naught power some square cube in general n plus 1, what happens? If f of z is analytic function in and on a within and on a closed curve C, and if z naught is any point within C, then f nth derivative of z naught is equal to n factorial by 2 pi I into lower C f of z by z minus z naught whole power n plus 1 dz. So these two things are the Cauchy integral formula, and it is generalization. So they are very important for us. And one more theorem we have, Morera's theorem. If f of z is continuous in a domain D, and if integral over C f of z dz 0, then f must be analytic. It is the converse of Cauchy's theorem. What Cauchy's theorem says is, if f of z is analytic in a domain and C is any closed curve in C, then integral over C f of z dz becomes 0. Here what it says, if f of z is continuous and integral of f of z dz is 0, then f must be analytic. It is a converse of Cauchy's theorem. Then there are some problems on Cauchy integral formula. C is mod z is equal to 4. Only thing we have to check is, in these problems, first you have to focus on the denominator. Why? The points at which the denominator goes to 0 are very, very important for us. They are called singularities. At those points, the function goes to infinity or does not exist. Our function is not analytic. We have to focus on those points. First, then make the denominator 0. They are called poles, a singular point, whatever it is. So then check whether these points lie inside the given region or not. If they are outside the region, don't worry, integral becomes 0. If at least one of them lies inside, then you have to apply Cauchy integral formula. If the point lies outside, Cauchy formula, Cauchy theorem. If the point lies inside, Cauchy integral formula. Okay, very simple. So mod z is equal to 4 is a circle with center at 0, 0 and radius 4 like this. And what is the value of denominator at which it goes to 0? Say for example, z minus 2 is equal to 0 or z is equal to minus 2. Where z is equal to 2. Z minus 2 is equal to 0 or z is equal to 2. So have an idea of the circle. Center z 0, 0 and radius 4. And what is the point? Z is equal to 2. Z is equal to 2 lies outside the region or inside? Inside the region here. So then it can apply Cauchy theorem. Cauchy theorem is applicable only when the function is completely analytic. It's not so now. This z minus 2 is giving the problem. So this comes under this statement, f of z by z minus z naught dz. We have to apply this. This is in the form. So f of z is 2z square plus 5 by z minus 2. Then by Cauchy integral formula, f of z naught is equal to 1 by 2 pi I integral f of z by z minus 2. So I'm sorry, z minus 2. This one z minus 2. We have done mistakes here. Z minus 2 is 9 and 3. Answer. Z minus 1 is equal to 3. So first we have an idea whether the point lies inside or not. See, if you can draw the diagram, very fine. Otherwise what you do is, what is the point here? Denominator at which denominator becomes 0, z is equal to minus 1. Do one thing. You find the point at which denominator becomes 0, substitute in the curve. What happens if we put z is equal to minus 1 this point here? What happens? Modulus of minus 1 minus 1. What is modulus of minus 1 minus 1? Minus 2. Modulus of minus 2 is square root of 2. Less than 3 or not? Less than 3. Less than the right hand side 3, then it lies inside. Say for example, if you have z plus 4 here, then what is the pole here? Z is equal to minus 4. If you put z is equal to minus 4 here, what happens? Minus 4 minus 1, 5. What is the magnitude of 5? 5 is greater than 3? Greater than 3. So it lies outside. This is one simple test. You substitute the point at which the denominator becomes 0 in the given curve. If it is less than the right hand side, it is inside. If it is greater than the quantity, it lies outside. That is a simple test, you can do it. So clearly z is equal to minus 1, we put it here, modulus of minus 1 comma minus 1 minus 1, that is minus 2 is clearly less than 3. So z is equal to minus 1 lies inside. So it's in the form, we have a problem with this denominator. So into over C f of z by z plus 1 power 4. This is the formula, generalized Cauchy integral formula. So this part we have now, f of z by z minus z naught power n plus 1, but I have here 4, so n is 3. N plus 1 is 4, so n is 3. So the formula becomes f triple derivative of f of z naught, okay, is equal to 3 factorial by 2 pi I into f of z by z plus 1 whole power 4. So f is e power 2z, f dash is 2e power 2z, f double dash is 4e power 2z, f triple dash is 8e power 2z. So this integral becomes 2 pi I by 3 factorial into triple dash of f is 8e power 2z, and the point z is equal to minus 1. Straight away you can calculate the integral. You can need not evaluate the usual integration and all that. Straight away you can put in the formula. You evaluate e power minus z by z into z plus 3, where mod z is equal to 4. So the denominator becomes 0 at z is equal to 0. Okay, and z is equal to minus 3. And the curve is mod z is equal to 4. Z is equal to 0 is clearly inside the circle. Z is equal to minus 3 is also mod minus 3 is less than 4, lies inside. So, but Cauchy integral formula says f of z by z minus z naught only, but we have z into z plus 3 denominator. So we split that into partial fractions so as to apply Cauchy integral formula. So e power minus z by, you split this into partial fractions, 1 by 3, 1 by z minus 1 by z plus 3. So this is what we have. So for each of these things, apply Cauchy integral formula, and then this is the answer we get. Then we have complex power series. Complex power series. So infinite series of complex numbers. What do you mean by infinite series of complex numbers? Let sigma zn where equal to z1 plus z2 plus so on and so forth, zn so on and so forth is an infinite series of complex numbers. So let us say each z is a complex number, obviously. So let's call them as zn is equal to an plus I into bn. Okay, so then what happens to sigma zn? Sigma an plus sigma I bn, I into sigma bn. Sigma zn becomes sigma an plus I into sigma bn. Again, that means sigma an and sigma bn are now real series, infinite series of real numbers. Okay, so these infinite series of real numbers sigma an and bn, if they are convergent to, let us say, capital A and capital B respectively, then the sigma zn converges to A plus IB. This an converges to A, this bn converges to B, so zn converges to A plus IB. And as usual, whenever the sigma zn converges, then nth term of the series goes to 0. Limit n goes to infinity, zn becomes 0. Limit n goes to infinity, zn goes to 0. So then power says a series of the form sigma an into z power n is called power series. If this power series converges for mod z less than r and diverges for mod z greater than r, then r is called radius of convergence, and the region mod z less than r is called a region of convergence, and mod z is equal to r, the curve. See, mod z less than r means all the points lying inside the curve circle. That means it's a region. Okay, that's what region of convergence. If it is lying outside that circle, it is a region of divergence. We don't discuss region. That's not important for us. And then the line, the curve, mod z is equal to r, that is called circle of convergence. Okay, radius of convergence is very important. For every problem in infinite series, we have to mention the region of convergence or radius of convergence. We have two wonderful theorems here. One is Taylor's theorem. The first one is the basic again. Taylor's theorem in complex numbers. Which goes like this. Let C be a circle with center at Z0 and radius R. Let f of z be analytic at all points within C. Then for any function. So you have to understand this Taylor's theorem, and next one is Lorentz expansion. The difference between these two. First I am telling Taylor's theorem. Taylor's theorem, the most important thing is f is analytic completely analytic. Then only we can write the function as a Taylor series. The function must be completely analytic. Let f of z be analytic at all points within C. Then for any z inside C, f of z is equal to f of z0 plus f dash z0 plus into z minus z0 plus f double dash z0 into z minus z0 z square by 2 factorial, so on and so forth. Nth derivative of z0 into z minus z0 power n by n factorial, so on and so forth. Or else you can write f of z is equal to sigma n is equal to 0 to infinity fn z0 by n factorial into z minus z0 whole power n. This is very much similar to what you have learned in Taylor series in one variable calculus. This is a Taylor series expansion of f of z around z0. So this wording is very important because at times express Taylor's expansion around z is equal to 0, around z is equal to 1, around z is equal to pi. This type of problems you may get. So this expansion is about z is equal to z0. Then how to identify whether the given expansion is about z is equal to z0 or not? So if you see the terms here, the polynomial z minus z0, z minus z0 square, z minus z0 power n. That means the expansion is about z0. If z minus 1, z minus 1 square, z minus 1 cube, so on so terms, that means expansion is about z is equal to 1. If I simply have z, z square, z cube, so on and so forth, expansion about 0. So the Taylor series expansion around about z is equal to z0. Then comes Maclaurin series expansion of f of z. If you expand this Taylor's theorem about 0, then that is called Maclaurin's. That means put z0 is equal to 0. What happens? Then f of z is equal to z0 is 0, f of 0 plus f dash 0 into z plus f double dash 0 into z square by 2 factorial, f triple dash z cube by 3 factorial, so on and so forth. This is called Maclaurin series expansion. This is very important because any function you can simply, if you know the function value f of 0, f dash 0, f double dash 0, you can write the function as an infinite series. That's how this e power z, sin z, cos z, sin hz, cos hz, name anything, any function. The expansion of such functions are derived from Maclaurin series expansion only. Let us see, using Maclaurin series expansion, we can establish some important formulae. So expansion of e power z is 1 plus z square by 2 factorial plus z cube by 3 factorial, so on and so forth. You can simply write it as sigma n from 0 to infinity z power n by n factorial. Similarly, sin z minus z cube by 3 factorial plus z power 5 by 5 factorial minus z power 7 by 7 factorial, so on. So these things, all these things can be obtained using Maclaurin series expansion. Cos z is 1 minus z square by 2 factorial plus z power 4 by factorial minus z power 6 by 6 factorial, so on and so forth. So 1 by z, these two things are very important for us. For the Lorentz expansion, these two things are very important. 1 by 1 plus z, or this is 1 plus z whole inverse is 1 minus z plus z square minus z cube plus z power 4, so on and so forth, or else minus 1 power n z power n. This series is valid only when mod z less than 1. So this means this is the region of convergence. This is the region of convergence. And then is 1 by 1 minus z is 1 minus z power minus 1. Simply can write it as 1 plus z square, so on and so forth. Or else this minus 1 power is not there here. So simply sigma z power n for mod z less than 1. These two things are very important. Now, expand f of z is equal to 1 by z square in powers of z plus 1. That means expansion about z is equal to minus 1. Don't worry, it is very simple. Let us say I want this in terms of z plus 1, call this as some w. So what happens to z now? W minus 1. So now f of z becomes 1 by z square is equal to 1 by w minus 1 whole square. Or you write 1 minus, because the expansion 1 by 1 plus something you know. So this is simply 1 by 1 minus w whole square, or 1 minus w whole power minus 2. This is same as 1 plus 2w plus 3w square, so on and so forth. And mod w less than 1 is region of convergence. Now substitute this w back. What is w? Z plus 1. So you get 1 plus 2 into z plus 1 plus 3 into z plus 1 whole square. Now what are the powers here? Now it's clearly it's in the powers of z plus 1. This is what is required. And the region is mod w less than 1 here. So w is mod z plus 1. So if you put z plus 1 here, mod z plus 1 is less than 1 is the region of convergence in this case. So next problem, f of z by z minus 1 into z minus 3 in powers of z minus 1 when 0 less than mod z minus 1 less than 2. So we have to convert first everything into w first to make the problem easily. So let us say w is equal to z minus 1. So then function becomes z is w plus 1 by w. The z minus 3 becomes w minus 2. Then split this into partial fractions. We get minus 1 by 2w minus 3 by 4, 1 minus w by 2. Because when I say z minus 1 is less than 2, so mod w less than 2. But when you write this 1 by 1 by something power minus 1, this thing 1 by 1 minus z, this is the region. The radius should be, radius of convergence must be less than or equal to 1. Okay. So whenever mod w less than 2, I need 1 here. Then only the series converges. Maximum radius must be 1. So divide this. Then what happens? Mod w by 2 will be less than 1. So the term should be in terms of w by 2. Then only the radius will be, radius of convergence will be 1. So that now what I do is from this, I take 2 minus 2 common. This becomes 1 by 1 minus w by 2. So that if you write a series 1 plus w by 2, w square by 4, and this modulus of w by 2 is less than 1, the series converges. So at the end, substitute w is equal to z minus 1. Mod z minus a is equal to r2, where r2 is less than 1, r1. Like that means here, like both are centered at a. See the difference. Both are centered at a, different radii. So two concentric circles centered at a. This is r2, radius r2, this is radius r1, and r2 less than r1. This is, now let f of z be analytic on c1, on c2, and throughout the region bounded between c1 c2. That means just like this is like vada, we eat no, also vada, it's like vada shape. This is what we call a ring shaped region. It's called a ring shaped region or annulus region. Okay, this shaded part is called annulus. So F is analytic in such an annulus region. That means this region is eliminated. Then Z be any point in the ring shaped region like this. Then f of zb can be expressed as sigma n from 0 to infinity a n z minus a whole power n from plus sigma n from 1 to infinity b n by z minus a power n. So mind you, what is the meaning of this is, let us say I have a complete plane, circular region like this, but I have a pole here. That means the function goes to infinity or maybe not analytic here at this point, singular point or maybe pole. So what I do is, in general, when I have a point, I like this, what I do is, this point, draw a small circle around that point, you remove that point. Remove means you need not remove it, neglect that point. So what is the remaining circle? So it is an annulus region. So this is what I said. Whenever the function has some singularities or poles inside, see what to do, can't do, write the expansion of the function. Yes, we can do. You construct a small neighborhood around the point, neglect that small neighborhood around that pole. then the remaining region becomes annulus region. Okay. So Lorentz series does not, the statement does not involve this word like polar singularity. It talks about the regions in annulus region. Then we apply this to poles and singularities. So whenever a function is analytic in annulus region, the function can be expressed as like this. If you observe the first term here, it is same as a Taylor series. It is same as Taylor series. And z minus a power n, positive powers. And if you observe the second term, and also Taylor series is when the function is analytic. This is Taylor's form. So this part of the Lorentz series is called analytic part. Why? Because it is same as Taylor series, which is possible only when the function is analytic. This part is called analytic part. The second part, if you observe, an is here, bn is here, no problem. But z minus a power n, positive powers of z minus a, here we have 1 by z minus a power n or z minus a power minus n. So we have negative part here, negative powers of z minus a. So Lorentz series expansion contains two parts. One is positive powers of z minus a and the other one is negative powers of z minus a. These two things are, they together they contribute to Lorentz series expansion. So because this is a negative powers of this z minus a, that part is called principal part. So where an and bn are given by 1 by 2 pi into lower c, f of z by, or f of s, z dash is not derivative here, some other variable, f of s by s minus a power n plus, or f of w by w into lower c. Lower c means Taylor series. Okay, expand f of z is equal to 1 by z square minus 3z plus 2 in the region 0 less than mod z minus 1 less than 1. So f of z is equal to z minus 1 into z minus 2. So we have to apply this Lorentz series. First we have to split this into partial fractions, that is 1 by z minus 2 minus 1 by z minus 1. So whenever you expand this function as Taylor series and Lorentz series, you have to be very particular about this series of convergence. So first thing is 0 less than mod z minus 1 less than 1. In this region, I write this as 1 minus 1 by z minus 1 by 1 minus z minus 1. So this becomes minus whole power minus 1. The formula we have, use this formula, and then see here, they're all positive powers. In the last step we have negative power. Z minus 1 power minus 1. This is B1. Lorentz principal part. So in the region mod 1 less than mod z less than 2, 1 by mod z less than 1, and mod z by 2 less than 1. So we see that the function, all the terms are in terms of 1 by z and z by 2. So 1 by z minus 2c, for example, you have to convert this into z by 2 terms. So divide by 2. So if you take 2 common, becomes 1 minus z by 2. And the second function, the relation we have is 1 by z is less than 1. So take z common. So 1 minus 1 by z. Then 1 minus z power minus 1, and this becomes 1 minus 1 by z power minus 1. So this is powers of positive powers of z, and in this we have negative powers of z, and this becomes our principal part, and this is our analytic part, and the Lorentz expansion. So similarly, some other problems I have worked out to do this. And then zeros and poles. We are coming towards the end of the presentation. The last topics, the zeros and singularities, poles, and residue theorem, called residue calculus or theory of residues. Zeros and poles. A point z0 is called a zero of an analytic function f of z if at that point the function becomes 0. And a point is called a singular point if f of z fails to be analytic at that point. Just like I said, everywhere around in this region it is analytic, but at a point it is not. So that is a singular point. Then say for example f of z is equal to 1 by z minus 1. At z is equal to 1, the function is not defined. So that is a singular point. Isolated singular point. So it's a singular point satisfying some property. What is the property? If singular point z0 is called isolated singular point if there exists no other singular point in a neighborhood of that z0. Isolated single point. So if it is one point is there is no other point in the neighborhood of the z0 point. It's an isolated. So that is called isolated singular point. Classification of isolated singular points now. Let it expand it as a Lorentz series. As I said earlier, whenever we have single points inside the C, we can always express it as a Lorentz series. One is analytical part and the principal part. The series contains two parts. This first one is analytical parts with positive powers of Z minus Z naught, and it's called analytical part. The second one is negative powers of Z minus Z naught, is called principal part. So in the classification we have removable singularity, poles, and essential singularity. Then what is removable singularity? If all Bn's here, the principal part, are 0, no negative powers of Z minus Z naught, then Z naught is called removable singularity f of Z. So f of, and that is f of Z can be made analytic by redefining f of Z suitably if limit Z goes to Z naught, f of Z exists. So that means, so when Bn becomes 0, function is analytic kada, why we are calling it as singular point. Okay, so you can make these Bn's, you don't observe these Bn's here in this series, but by suitably redefining the function, you'll see an example, understand a better way. Okay, by redefining this function suitably, you can remove a singularity. It is a singularity, but it can be removed by redefining the function appropriately, suitably. That's why it is called removable singularity. The second one is essential singularity. If the principal part contains infinite number of essential singularity, you cannot avoid it. Essential. So if the principal part contains infinite number of terms containing negative powers of Z minus Z naught, then Z naught is called essential singularity. Okay. First case, zero negative terms, but still is a singular point. Here it is infinite number of negative powers of Z minus Z naught, then it is called essential singularities. Okay, so and then pole of order M. If the principal part of Lorentz series, understand very clearly, when there are 0 terms in negative powers, it's called removable singularity. By infinite number, it's called essential singularity. What happens if finite number of negative powers? So that is called pole of order M. If the principal part of Lorentz series contains a finite number of terms, then Z naught is called a pole of order of M of f of Z. Since pole is a simple pole, means pole of order 1. Now let us classify the singularities 1 by Z minus Z cube. You can write this as 1 by Z into 1 minus Z square. As I said, equate this denominator to 0 and find the points, they are the poles. So Z is equal to 1, 0 and minus 1 are the poles of order 1. Okay. And cot 1 by Z minus 1 by Z. So cot 1 by Z is when Z is equal to 1 by k pi, 1 by Z becomes k pi. So cot pi, what is cot pi? Cos pi by sin pi. Sin pi is 0, goes to infinity. Okay. So whenever Z is equal to 1 by k pi, this cot function goes to infinity. So 1 by Z is equal to k pi, for k is equal to plus or minus 1, plus or minus 2, so on and so forth. They are all poles of order 1. And also Z is equal to 0. Whenever Z is equal to 0, what happens is Z is equal to pi. When k goes on increasing, what happens? Z becomes, this 1 by k pi goes to 0. So the 0 is nothing but a limiting point of 1 by k pi. So Z is a limiting point of the poles, or Z is equal to 0 is non-isolated. Why this becomes non-isolated is, it's a very important question. See, Z is equal to k pi, as k is plus or minus 2, plus or minus 3, so on and so forth, go on increasing. Then what happens to 1 by k pi? As k goes to infinity, Z goes to 0. So Z is equal to 0, a limit point of this 1 by k pi. So you cannot say there is no other singular point in the neighborhood of 0. There are. So Z is equal to 0 cannot be a isolated singular point. We call it a non-isolated singular point. Then theory of residues. It is very useful and as an elegant theory in complex integration. Residue means residue of an analytic function f of z at an isolated singular point z naught is the coefficient of 1 by z minus z naught and the Lorentz expansion of f of z about Z is equal to Z0. So if Z0 is in a singular point, isolate singular point, and then we cannot get a Taylor series, we get a Lorentz series expansion. In the Lorentz series expansion, the coefficient of 1 by Z minus Z0. What is the coefficient of 1 by Z minus Z0 from the series expansion? 1 by Z minus Z0, n becomes 1. So B1 is the coefficient of 1 by Z of Z at Z0. It is denoted by residue of Z is equal to Z0 f of Z. From Lorentz series expansion principal part, we know that B1 from that series is B1. But what is B1? Here. Where is that? B1 is 1 by 2 pi I f of integral of f of w by w minus a power minus 1 plus 1. This denominator becomes 1. So 1 by 2 pi I integral over c to f of w dw. B1 is 1 by 2 pi I integral c f of w. So from this, you can observe this. From this, you can calculate easily. Integral c f of z w, f of z dz is 2 pi I into B1. Where whenever you have singular point at the curve around this, the circle is surrounding this singular point, then this becomes B1 2 pi I into B1. So residue at z is equal to z0 is 1 by 2 pi I. B1, because B1 is the residue at z0 of f of z. So this is equal to 2 pi I into lower c f of z. So, or else into lower c f of z dz is 2 pi I into residue. This is the result. Thus, to evaluate integrals, residues are useful. So basing on this principle, we have residue theorem. We'll come to that later on. So if it is a singular pole, simply it is residue at z is equal to z0 is f of z by 1 by 2 pi I into lower c f of z. If it is calculation of residue at a simple pole, from Lorentz series expansion, z0 is a simple pole of order 1. So only 1 by z minus z0 exists in principal part because pole of order 1 kabatti. So pole of order 1 kabatti finite order ante we have only finite number of terms, that is we have only one term b1 by z minus z0, and b1 is, if you multiply throughout with, this is a Lorentz series expansion, throughout with z minus z0. So z minus z0 and f of z is equal to b1 plus sigma a n z minus z0 power n plus 1. As z goes to z0, if you take, because I want b1, all these terms become 0, and here left hand side limit z goes to z0 f of z minus z0 into f of z. So how do you calculate this b1? Limit z goes to z0 z minus z0 into f of z. You need not write Lorentz series, you need not find 1 by z, what is the coefficient of 1 by z minus z0. You need not do it. If z is equal to z0 is a simple pole, that means pole of order 1, so then residue at z is equal to z0 is simply limit z goes to z0 z minus z0 into f of z. If it is a multiple pole, then that what happens? In Lorentz expansion, you have m number of terms, finite pole. So then residue at z0 f of z is given by 1 by m minus 1 factorial, limit z goes to z0, m minus 1 the derivative of z minus z power m into f of z. You have to remember this formula, two things. If it is simple pole, multiply the function with z minus z0 and then limit z goes to z0. If it is a multiple pole, then multiply the function with z minus z0 power m, that means order of the pole, then m minus first derivative, take that, then limit z goes to z0 into 1 by m minus 1 factor. This is the formula. But when z0 is essential singularity of f of z, then the above formula fails. Then we have, then if it is essential singularity, then these formulas they won't work out. Then you have to find the Lorentz series, find the coefficient of 1 by z minus z0, that is b1. Then comes residue theorem. Now clearly if you see this b1, it is integral terms. So or else integral over c f of z dz is 2 pi I into b1. That means you can integrate the function Evaluate the integral in terms of the residues B1. So basing on that, this residue theorem is formulated. Let f of z be analytic within a simple closed path C, except at a finite number of singular points. Let's say I have a curve like this, but there are some finite singular points within the C. Z1, Z2, Zn inside C. Then draw small curves, circles around all these points, what we call neighborhoods. Then integral over C f of z dt is 2 pi I into sum of the residues. If you have only one simple singular point B1, if so many we have B1 plus B2, so many such points, then this is residue 1, residue 2, residue 3, and add all the residues. What is the integral? 2 pi I into residues. Okay. About C1, let us say B1 into 2 pi. About C2, 2 pi into B2. Nth pole, 2 pi into Bn. Add all these things, you get the results. So integral over C f of z dz is 2 pi I into sum of the residues. This is the called residue theorem. Classify singularities of e power z by is also one nice problem. E power z by e power z minus 1. So whenever denominator becomes 0, e power z is equal to 1, and when does this e power z becomes 1? Because cos 0 is 1 or 2 pi is 1. So e power plus or minus 2n pi I. 2n pi I, e power 2n pi I is cos 2n pi plus I sin 2n pi. I sin 2n pi is always 0, sin 2n pi is always 0, cos 2n pi plus or minus, that is 1. So singularities are whenever z is plus or minus 2n pi, e power z becomes 1, then singularities come. So that is one thing. Singularities are these things. Now let us see what we mean removal singularity and all that. This appears to be whenever z is equal to 2n pi plus or minus 2n pi, this is singularity clearly. That is clear. Okay, you cannot avoid these regular points. But what I said, removal singularity, by redefining the function suitably, we can remove the singularity. Let us see what we mean by redefine the function. So z by e power z minus 1 is e power z is 1 plus z square by 2 factorial minus 1, that can be cancelled. Z is there, the denominator throughout z is there. If you cancel that z, what happens is 1 by 1 plus z by 2 factorial plus z square by 3 factorial, so on and so forth. Now is z is equal to n pi is a singularity here now? No. Z is equal to 2n pi is not a singular point now here. If you define f of z by cancelling this z, this is same as this expression. So when you consider this as f of z, you don't see that 2n pi is a singular point here. So that means e power z by z minus 1 minus 1, therefore z is equal to G0, remove the singularity. So z is equal to 0 also. Whenever z is equal to 0, what happens? E power 0 is 1 and z minus 0 minus 1 minus 1 is 0. So z is equal to 0 is also singular point here. But if you define the function like this, you can remove the singularity and provided the limit exists. Limit z by e power z minus 1 exists. Okay. So z is equal to 0 is a removable singularity. Then why it is 1? Because if you put z is equal to 0, 0 by 0 form, then if you apply L'Hospital's 1 by e power z, 1 by e power 0, the limit becomes 1. So z is equal to 0 is a removable singularity. Evaluate integral over c z square plus 4 by z2 plus 3z 2z square plus 2z, where cg is equal to mod z plus 1 minus I is equal to 1. Let us use this residue theorem to apply these things. The poles are the roots of the denominator. So z2 plus 2z square plus 2z is equal to 0. You take z common, z square plus 2z plus 2 is equal to 0. Z is equal to 0. Z is equal to minus 1 plus I. Z is equal to minus 1 minus I. They are the roots of the denominator. So they are the poles. They are not repeated roots. They are simple poles of order 1. Simple poles means order 1. So let us see the geometry of that. The region is mod z plus 1 minus I is equal to 1. That means center of the circle is minus 1 I and radius 1. So minus 1 is this point, radius is 1. So the circle lies like this. And where are these points? Geometry, if you consider the points. So you can verify in two ways, as I said. If you consider the geometry, it's like this. Z is equal to 0 is here, outside the circle. Z is equal to minus 1 minus I. That means both x and y are negative. So x and y are negative means this is here, minus 1 is outside the circle. This third point is minus 1 plus I. This is center of the circle. So out of the three poles, Z is equal to 0, minus 1 minus I are outside the region. We need not care about it. Only point lying inside is minus 1, 1, that is minus 1 plus I. This is one way. The other way is substitute the points in the given point region. Say for example, if you put Z is equal to 0 here, what is magnitude of 1 minus I? When Z is equal to x plus iy, magnitude of z x plus iy is square root of x square plus y square. When you put Z is equal to 0, magnitude of 1 minus I is square root of 2 is greater than 1. So this point Z is equal to 0 lies outside. Coming to this second point, minus 1 plus I, if you substitute here, minus 1 plus I plus 1 minus I. So minus 1 plus 1 plus I minus the cancel becomes 0. Mod 0 is less than 1. So it lies inside. Third point, minus 1 minus I. Minus 1 minus I. So minus 1 plus 1 cancel. Minus I minus I minus 2I. So magnitude of minus 2I is square root of 2 greater than 1. So lies outside. That way also you can verify. So out of the three poles, only point lying inside is 0 and minus 1 plus I. So simple pole. So residue, no, the simple pole. Limit Z goes to Z0, Z minus Z0 and f of Z. Okay. So limit Z goes to minus 1 plus I, Z minus Z0 and f of Z. F of Z you can write as what is that? Z square plus 4 by the factors Z into Z plus 1 minus I, Z plus 1 plus I. This Z plus 1 plus minus I can be cancelled. So limit Z goes to minus 1 plus I, Z square plus 4 by this whole thing. If you put the limits, this is your residue. Then by residue theorem, what happens? If this is residue, the integral value is 2 pi I into residue. So the answer of integral C f of Z is 2 pi into residue. That is the answer. So this is how we can calculate the problems in integration residue theorem. There ends residues. The contour integration is there. It is not, I suppose, there in the syllabus, and it is becomes very lengthy also. And we cannot complete today. If we need one more day for that. So till now we have finished off so many things and complex things. Now let us see some problems on complex variables. Show that f of Z is equal to mod Z by Z is not continuous. We have done this problem already. First we can take x along x goes to 0, y goes to 0, y goes to 0, x goes to 0, two paths, the limits are different. F z is equal to mod is also, we have done this problem. Show that x square plus I into 2x minus y, f of z e power x plus I sin x square continuous for all z. F of z is z power n, where n is a positive integer is differentiable for all values of z, where n is positive integer. F dash z is limit delta z goes to 0, f of z plus delta z minus f of z by delta z. Then f of z plus delta z is z power n, z plus delta z power n minus z power n. We expand this and cancel z power n, then cancel the delta power z here. So here this term will be independent of delta z, this like this. In all the other terms we have delta z. So as delta z goes to 0, all these things become 0 and we have n into z power n minus 1. Show that real part of z is x is continuous but not differentiable. We know the x is always continuous function because it's independent variable, it's always continuous. Limit z goes to z0, f of z is equal to limit x goes to x0, y goes to y0 of x is equal to x0 f of z0. Coming to f dash z, x plus delta x minus f of Z is x by delta x plus I delta y, cancel x, so delta x by delta y, and then delta x goes to 0, it is 0. But if you reverse the limits, what happens? That means limit delta x goes to 0, delta y goes to 0, we get 0. But if you reverse the limits, delta y goes to 0, delta x goes to 0, when we first use the delta y goes to 0, this term becomes 0. Then what we have? Delta x by delta x becomes 1. Here the limit is 0, it is 1. So limits are not equal, hence the f is not differentiable. Find the derivative from the definition, similar problems. I don't want to repeat this thing. Find where the function, following functions are not analytic, fail to be analytic. If analytic avalante, the function must be differentiable at that point, around that region, around the neighborhood of the point. So if we can prove that f is not differentiable, that's enough. So w is equal to 1 by z, let us say, then dw by dz is minus 1 by z square when z not equal to 0. So for z is equal to 0, dw by dz does not exist. So the function is not differentiable, hence not analytic. Then the same thing with this also. If when you find the derivative, you get minus 1 by z minus 1 square, it fails. So dw equal to zq minus 4z plus 1, dw by dz 3z square minus 4 is a polynomial. It's always continuous and differentiable. So this function is always analytic in the whole complex plane. So it becomes an entire function. Entire function means the function is analytic throughout the complex plane, and it is called entire function. So similar problems like that. And to prove that is not analytic, we have done this problem already. So determine whether the function is, so in the examination they won't ask to determine the function 2x5 plus I into x square minus y square is analytic, not analytic, differentiable at z is equal to 0, or differentiable at z not equal to 0, or maybe analytic at 0, analytic at not analytic at 0, analytic everywhere. Some options, whatever is out of the 10 options we can give, out of which only one is correct answer. So first, this is u and v. U is 2xy, v is x square minus y square. So dou u by dou x is 2y, dou u by dou y is 2x, and dou u by dou x is 2x, and dou u by dou y minus 2y. Are they equal? Dou u by dou x is equal to dou v by dou y. So we have 2y minus 2y. So CR equations are not satisfied. See, but this is a polynomial. This is a polynomial. We think that u and v are polynomials, always continuous and differentiable. So is f of z, but it's not so. When you consider this as a complex function, u plus iv form, it need not be. Though they are individually, they are continuous and differentiable. When they are real and imaginary parts of a complex function, it need not be. They may not satisfy Cauchy-Riemann equations. F of z is not analytic. E power x into cos phi plus I sin y is holomorphic. Holomorphic is same as analytic, and find its derivative. So I said, when we want to prove that it is analytic, maybe they can use different words. Regular function means analytic, holomorphic means analytic. So different ways. So u is e power x cos y, v is e power x sin y. So dou u by dou x is e power x cos y, dou u by dou y is e power minus sin y, dou u by dou x is e power x sin y, dou u by dou y is e power cos y. Are they equal? Dou u by dou x is equal to dou u by dou y, and dou u by dou y is equal to minus dou u by dx. Both are equal. So CR equation satisfied, and then continuity you have to check. E power z is equal to e power x into e power iy, or e power z. Okay. So this you can write as e power x into e power iy. Isn't it? E power iy. So e power x into e power iy. So there is e power z. F dash z is e power z. Moreover, dou u by dou x, dou u by dou y, dou u by dou x, dou y. E power x is always continuous and differentiable. Cos x and sin x, cos y, sin y are always continuous and differentiable. So all the four partial derivatives of order 1 are continuous. So, and the CR equations are satisfied. So the function is analytic. Find k such that this is harmonic, and find its conjugate. Both the things asked. So Let us say conjugate means harmonic means Laplace equation dou square f by dou x square plus dou square f by dou y square must be 0. Find dou f by dou x. Find k such that, okay. So dou f by dou y, dou square f by dou x square, dou square f by dou y square. So if satisfies Laplace equation, that means 6x plus 6kx is equal to 0. So x into 1 plus k is 0, k is equal to minus 1. Then this becomes 0. That's the value of. So when k is minus 1, then f of xy becomes x cube minus 3xy square. So g of xy is a conjugate of f of xy. So dg is dou g by dou x dx plus dou g by dou y dy. But CR equations, because harmonic function means they are analytic functions, because dou g by dou x becomes minus dou f by dou y, so on and so forth, like this. And then x by dx plus 3x square minus 3y square dy. So this is exact differential equation, and then integrating that you get g. Or else you can apply Milne-Thomson's method also. Find the analytic function whose real part is e power minus x into JSON. We have done this problem, I need not do it again. This also. Find the analytic function whose real part is x by x square plus y square. F of z is equal to u plus iv, u is equal to given. Milne-Thomson method we have decided. So f dash z is, because u is given, I write f dash z in terms of u, dou u by dou x plus I dou u by dou x, in terms of u, dou u by dou x minus I dou u by dou y. So find dou u by dou x and dou u by dou y from this. This is what I get. So Milne-Thomson method, replace x by z and y by 0. So this is minus z square by z power 4, and this becomes 0. So minus 1 by z square if you integrate 1 by z plus c. U is equal to 4xy minus 3x plus 2 is harmonic. Consider the corresponding analytic function u plus iv. Okay, u is equal to 4xy minus 3x, dou u by dou x is 4y minus 3, dou square u by dou x square is 0. Show that is harmonic. So similarly find dou square u by dou y square is 0. So dou square u by dou x square is 0, dou square y by dou y square is 0. So sum of them is 0. So Laplace equation is satisfied, hence harmonic. And construct the corresponding analytic function. So because u is given, f dash z is dou u by dou x minus I into dou u by dou y. So this f dash dou u by dou x and dou u by dou x is 4y minus 3, and dou u by dou y is 4x minus 4x. This is what we get. So by Milne-Thomson method, replace x by z and y by 0. This becomes 0 minus 3i minus 4iz. That is f dash z. So fz becomes, integrate this. That's all. E power z square is entire function. You can do it. Analytic everywhere. You can see. E power z square is e power x square minus y square plus 2xy. And the real part is when e power x square minus y square, e power 2xy, e power x square minus y square into e power 2xy is cos 2xy plus I should dxy. Then what is u and v? Then check the CR equations. So that's how are satisfied. And first partial derivatives, if you see, e power some function, exponential function is always continuous, and sine and cosine function are always continuous. So all the conditions are satisfied, necessary and sufficient conditions are satisfied. So hence f is. Then evaluate e power 2z by z minus 2 when z is 1. As I said, z is equal to 1 is centered at 0, radius 1. The point z is equal to 2 is outside the region. So the function is completely analytic. By Cauchy's theorem, integral becomes 0. E power z is analytic everywhere. So its integral is 0. Z square minus z plus 1 by z minus 1. Mod z is equal to 1 by 10. 1 by 2. So the radius is 1 by 2 centered at 0. But the point is z is equal to 1 outside the region. Okay, that is 1 is outside this circle with radius 1 by 2. So integral becomes 0. dz by z minus 2 around mod z minus 2 is equal to 4. What I said, the denominator z minus 2 is 2. At z is equal to 2, this is the pole. See, okay. You substitute here, what happens? 2 minus 2, 0 less than 4, so lies inside. Whenever it lies inside, then we have to apply Cauchy integral formula 2 pi I into f of z naught. What is f? This is f of z by z minus z naught. So f of z is 1 into 2 pi I. Let C denote the boundary of the square whose sides are so and so forth. Then evaluate each of the integrals. E power minus z by z minus pi I by 2. So z is equal to pi I by 2 is the root here, hole here. Whether it lies inside these things or not. So this is the circle here. So z is equal to pi I by 2 is a singular point. So is a imaginary axis at distance of less than 1 by 6. Pi I by 2 is this point here, somewhere here. Okay, inside the region. So e power minus z dz by z minus pi by 2 is in the form f of z by z minus a, where f of z is equal to e power minus z is equal to 2 pi I into f of a. This is Cauchy's integral formula. So substitute this pi I by 2 in e power minus just this thing, 2 pi I into e power minus pi I by 2. So cos pi by 2 minus I sin pi by 2. This is 2 pi. So cos z by z into z square plus 8. So z is equal to 0 is one singular point. Z square is equal to minus 8, or z is equal to square root of 8i. Okay. Within the square, hence take f of z is equal to this thing. Then this is what we get. Z square plus 8, z is equal to plus or minus 8i, square root of 8i. They are outside the region. So you take this as f of z and then f of a cos z by z square plus 8 at z is equal to 0. Then similar residues at Cauchy's integral formula. Some more problems on Cauchy's integral formula. You can do it. So I'll shift to residue theorems once. So there are problems on Lorentz series, Taylor series, maybe Cauchy integral formula. The most important thing is we have Cauchy residue theorems. Okay. There are all problems on Lorentz series. You can leisurely you can go through all the problems. There for some find the residues. Find the poles of the function. F of z is 1 by z plus 1 and z plus 3 and the residue z 3 poles. Given function poles in z is equal to minus 1 and minus 3 are the. So residue f of z is limit z goes to minus 1, z plus 1 into f of z. So z plus 1 cancels, 1 by z plus 3, so 1 by 2. Residue at z minus 3 is limit z goes to minus 3, z plus 3 into function. This is what, how we calculate it. Integration, let us see some problems later. Yeah, integral c z minus 1 by z plus 1 whole square and z minus 2. So c is mod z minus I. The poles are z is equal to minus 1 of order 2 and z is equal to 2. And minus 1, if you put it here, minus 1 minus 2. Z is equal to minus 1 is after second pole, a simple pole. C is equal to mod z minus I is equal to a circle with center I and radius 2. So C is enclosed the only pole at z is equal to minus 1. Z is equal to what happens? Z is equal to 2. It outside point. So only pole that encloses is z is equal to minus 1. So is a pole of order 2. So we have to apply this formula. Z goes to z naught d by dz z minus z naught square f of z. So this is what I get. So I think with this I conclude complex variables. We shall meet again tomorrow with concepts on probability. I sign out today. Thank you.